Hello, thank you so much for tuning into my YouTube channel. Today's video is going to be a tutorial on how to measure spectral similarity in MATLAB, which can be used in hyperspectral image classification as well, because even in that we measure the similarity of each pixel with respect to our end members. Let's get started and see how we could do that.
As I said in this video, I want to talk about how we can measure spectral similarity in MATLAB. There are different ways to measure the spectral similarity between two spectra in MATLAB. There are 5 different methods you can use to estimate the spectral similarities between the two spectra in MATLAB. In this video, I want to show you how you can use these methods for hyperspectral image classification as well. For that, we first need to extract the end members from the image and then specify the similarity of each pixel with respect to these end members. We then use these similarities to assign the pixels to a specific class of end member, which in turn leads to a hyperspectral image classification. These 5 methods are sidsam, ns3, sidsam, and jmsam. Sid just simply measures the spectral similarity using spectral information divergence. The sid function normalizes the reference spectra and the test spectra and computes the sid value using this formula, where Q and P are the vectors of normalized reference and test spectra. SAM measures the spectral similarity using spectral angle mapper. Given the test spectra T and the reference spectra R, the SAM score alpha is calculated as shown here. NS3 on the other hand measures normalized spectral similarity score. This method computes spectral similarity based on the Euclidean and SAM distances between the two spectra. Here R and T are the reference and test spectra respectively. We first calculate the Euclidean distance between the two spectra, and then we compute the SAM value alpha. Finally, NS3 is calculated as shown here. sidsam measures spectral similarity using spectral information divergence and spectral angle mapper. We first measure the spectral angle mapper. Here R and T are the reference and the test spectra respectively. And then we calculate spectral information divergence. P and Q are the vectors of normalized reference and test spectra respectively. And then sidsam is calculated using this method as shown here. In other words, just multiply the sid by the tangent of alpha, which is the SAM score. And finally, jmsam measures the spectral similarity using Jeffreys Matsushita and spectral angle mapper method. First, we compute the jm distance as shown here, where b is a Bhattacharya distance as shown here. R and T are the reference and the test spectra respectively. Mu sub r and mu sub t are the mean values of the reference and test spectra respectively. Sigma sub r and sigma sub t are the covariance values of the reference and test spectra respectively. Then we also calculate the SAM value alpha by using the test spectra T and the reference spectra R. And finally, jmsam is calculated using this formula. Let's go to MATLAB and see how we can apply these methods. Okay, let's first start with the sid method. This is the data we're using. And here we're going to extract the end members. We first estimate the number of end members and then we extract them. This method estimates the end member signatures by finding a simplex of a volume on the reduced data. And this is where we're going to show the end members. And now using sid, we're going to find out the similarity of each pixel to the end members. And then using that, we're going to classify the hyperspectral image. Let's run this. So these are the end members. And then we use these end members to classify this hyperspectral image using sid method. You can see there are 10 end members in this hyperspectral image. Now let's go to the spectral similarity using SAM. So we first again read the data, and then we specify the number of end members, and then we extract them. But now here we use SAM to calculate the similarity of each pixel in the original hyperspectral image to the end members that we extracted here. So the result of our SAM calculation is our classification map, as you can see here. So let's run this one too. We can see here again we have 10 end members, and this is the result of classification using SAM. Now we're going to do the same thing but with NS3. We have the same data and we're going to first extract the end members, but here we're going to use NS3 to calculate the similarity of each pixel to the end members, which would lead to our map of classification. Let's run this as well. You could see here these are our end members, and this is the result of classification using NS3 method. Now we're going to use sidsam. Again, we use the same data, but here to calculate the similarity between each pixel of the hyperspectral image and the end members, we're going to use sidsam, and the result of this is going to be our map of classification. Let's run this and see what happens. You could see here these are our end members, And this is the result of the classification using sidsam method. And finally, we're going to use jmsam. So again, we read the data, we specify the number of n members, and then we extract them. And here we use jmsam to calculate the similarity of each pixel in the hyperspectral image to our n members. And the result of this is going to be our classification map. Let's run this. These are again our n members, and this is the result of classification using jmsam. And that's about it. This was a very quick introduction to 5 different methods that you could use to calculate the spectral similarity between each pixel in the hyperspectral image and the n members.
Thank you so much for watching this video. I hope you liked it and you were able to get something out of it. If you liked it, I would appreciate it if you could subscribe to my channel and also share the video with your friends. Thank you so much and have a nice day.